Hi, my name is Rebecca Agapov, and I'm a graduate student in the Department of Polymer Science at the University of Akron. Right now, I'm standing in the laser lab of the Goodyear Polymer Center. This lab has been specially designed for doing experiments with laser light. Over the past 50 years, lasers have become a valuable and essential part of our daily lives. You can find lasers at work in many different places, like the cash registers at the grocery store and in your common CD and DVD players. You also see lasers on display as light shows during concerts, and they're commonly used to perform some medical procedures such as corrective eye surgery. Lasers can also help scientists determine the size and chemistry of unknown substances. In our lab, we use a technique called Raman Spectroscopy, which involves shining laser light onto a sample to obtain the fingerprint or chemical identification of the sample. Our experiments are performed on this optical table, which floats on air to help us minimize vibrations from the room. We then generate our light in this laser tube, which exits here, passing through several optical elements before it's focused on our sample over there. We use several different optical elements to optimize our beam for experiments. First, we pass our beam through these beam splitters to decrease our intensity. This prevents us from burning our sample. We also use several different mirrors to change the direction of our beam. The light strikes here and then here, allowing us to direct the light onto our sample. If these mirrors weren't in place, the beam would go straight ahead and strike the wall instead of our sample. The light that scatters back from our sample gets passed through these optics and collected in this special camera. The data we get can then be plotted like the spectrum shown here, which is intensity as a function of energy. This spectrum can give us the fingerprint identification of the chemistry of whatever the sample is we're looking at. This spectrum is from polystyrene. Polystyrene is commonly found in styrofoam plates and cups, as well as in egg cartons. As part of my research work, we are working to improve the sensitivity of Raman spectroscopy so that we can reproducibly get signals from very small amounts of material or even single molecules. This can open up new avenues of chemical sensing, such as biological threats and weapons of mass destruction. It also will allow real-time biological imaging of cell interactions and even real-time imaging of corrosion processes, such as salt and water eating through the aluminum on airplanes. In real life, scientists need to be able to manipulate the laser beam so that we can get it to strike a sample. To demonstrate some basics behind lasers and optics, we're going to do this today using some basic mirrors, a styrofoam cup, and a laser beam that you can find at any office supply store. When you take the laser beam and strike it directly at our camera, which today will be a target, we can see the laser on the target. Now we place a styrofoam cup in the beam path, blocking the beam from the target. For this demonstration, we will use the mirrors to manipulate the beam around the styrofoam cup and still strike the target. An experiment like this requires some trial and error. It will take several times to get all of the mirrors at the correct angles. It's also difficult to see the laser beam traveling through the air with our naked eye. To make it easier to find exactly where the laser beam strikes the mirror, you can use a sheet of paper standing in front of the mirror. Now that our mirrors have been properly aligned, we can redirect the laser beam around the styrofoam cup using these mirrors to still strike the detector, just like this. Scientists use this principle every single time they align a system to do a laser experiment. Well, I hope you had some fun learning about Raman spectroscopy and the science behind lasers. My name is Rebecca Agapov, and this has been another episode of the AGPA's Research Connection.